My name is Nicolas Espina, and my technical brief is Application Techniques to Reduce Shrinkage in Concrete. One of the biggest problems in concrete is the effects during the time that occur inside its particles. And concrete undergoes three main types of time-dependent volume changes, which may cause stresses, cracking, or deflections that affect the in-service behavior of reinforced concrete structures. These phenomena are creep, thermal expansion, and our focus shrinkage. Shrinkage, basically, shrinkage is the decrease in the volume of concrete during hardening and drying under constant temperatures. And there are three types of shrinkage. The first one is drying shrinkage, that is due to the loss of a layer of absorbed water. This loss has little effect on the magnitude of the shrinkage. The second is the autogenous shrinkage. Um, this is the self-created bulk strain of cement, past mortar, or concrete during hardening at constant temperature, and may result in formation of cracks that impair strength and durability. And in the next techniques, the purpose is avoid this shrinkage, this autogenous shrinkage. The last one is carbonation shrinkage, uh, which is basically the shrinkage caused by carbon dioxide rich in rich atmospheres. Um, the causes of the shrinkage are cement content, curing and storage, water cement percentage, coarse aggregate, and cement content and type. This figure show the shrinkage behavior and show this is a plot of concrete strain versus time. The strain starts at zero at the start of drying. The the strain increases with an ascending parabolic shape, and his strain would continue increase with a slope approaching to zero, where all the strains would be associated with shrinkage. Um, in the new techniques, we can find that these researchers find the shrinkage based on some experimental tests. Um, so we're going to summarize some of them because there are a lot of tests, but we're gonna use just three. The first one is the ASTM C1698-09. That is the standard test method for autogenous strain of cement pasts and mortar. This test basically is measures the bulk strain of a sealed cement past of mortar specimen at constant temperature and not subjected to external forces from the time of final settings until a specified age. And this is the equipment. In the foreground, corrugated PE mold and in the background the dilatometer. The second one is the free shrinkage test, which is that in based on some researchers before they calculated the shrinkage in specimens, in wall specimens. So they just find the strains, measure uh, every 7 days. And the last one is the evaluation of shrinkage cracking characteristics. This is based on on a rectangular mold with a hole at both ends. Um, the drying shrinkage in this case was measured for 60 days under constant temperature and humidity. Now, this is the first one of the techniques that I selected for the research. The first one is the carbon nanotubes, reinforced cement-based materials. These nanotubes are attracted because they have excellent mechanical properties. Because these carbon nanotubes or CNTs have have been combined with cement materials and improve performance in terms of electricals, durability, and hydration aspects. For that reason, in this research, also find a relation between the water cement ratio and the CNTs. As we can see in the follow chart, we can see the results about this research, and we can see that they use the colors means, for example, in the first curves, the colors means the proportion of CNTs, and each one of this group of curves are 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 based on the water cement ratio. The in this in this in this research, we can see that the CNTs works better with more water cement. So you can see that the first graph uh, has a better performance in the shrinkage strain than the others. The second research is the fiber reinforced cement composites using cellulose nanocrystals. In this study, they produce a high toughness cement composed reinforced with flax and steel fibers to improve the stencil deformation capacity and also drying shrinkage and strength characteristics. In this case, they vary the cellulose nanocrystal or CNCs between 0.4 and 1.2. So in the next graphs we can see it, and we can see that that the when we see the second with flax fibers, we see that it works better than the rest, regardless the the amount of CNFs, CNCs we take. The next one is the steel chip reinforced and polymer cement mortar. Is both of them. In this research, we can find what happened with both of the materials. And as we can see, the curve with the triangles is the PCM and SCP without them, without both the chemicals and the materials, and the circle curve is with them. So as we can see, we can see a better performance with them. But in this research, we can find also an interest predicting model based on 2D analysis. So as we can see, this is the two equation to find the shrinkage. So as we can see, we have these two equation, that is this expression with C1, that is an specific parameter for PCM or SCP. We have the 28-day compressive strength. We have a beta that is related to relative humidity. We have the age in days. Also we have the A sub C, that is the cross-sectional area of member. The T sub 0, that is the age when it's loaded. And we have U, that is the length of bar in contact with outside air. And we can see that these two equations prove and we can see that it depends of what we saw in the beginning of the presentation. And the final thing is the comparison between all these graphs and these curves. As you can see, this is the combined graph with all the curves. As we can see, and this will be some conclusion and some quick comparison between these three researches. I've just shown in the figure, we can take two shrinkage curves from the first research, which is the one with water cement ratio equal to 0.3 and 0.4. That is the blue one, and the red one. We also have the curves from the second research with behavior similar to the other curves. That is the orange one and another red. Additionally, we have two of the third research with the PCM and SCP. That is the purple one and the red one. But basically, we can say that all of these curves show three-stage distributions. The first stage was the first 8 hours. during which the sample contracted rapidly in the carbon nanotubes and PCM in an SCP in specimen, because remember that the third research has PCM and SCP out, but in this case it's PCM and SCP in. We can show that in the orange. The second stage depicted slight expansion between 8 and 12 hours, because as you can see here, this is the moment where contract, but then we can find this expansion, this little expansion, but on the contrary, we can see a first expansion in the cellulose nanocrystal and the PCM and SCP out specimen. And finally, in all the curves, we can find a smooth contraction after the 12 hours. We can see that in carbon nanotubes, the shrinkage inhibition ratios reach 20% and 40% with an equal with a water semen ratio equal to 0.3 and 0.4 respectively. Water semen ratio illustrated certain influence on the shrinkage effect of CNTs, to be specific to the first research. The drying shrinkage test revealed that shrinkage decreased in all specimens with CNCs were used. The shrinkage strain associated with the incorporation of flat fibers was lower than with just CNC. And finally, the curve shows that applying CNCs has a better performance than CNT or PCM and CNC SCP. But to end this presentation, in conclusion, it is a necessity to continue doing researches about shrinkage, because we need to know more about it.